Hello again everybody! In today's video, I would like to discuss Newton's 3 laws of motion. Let's begin on the first law. An object that is at rest will remain at rest, or an object that is moving will continue to move in a straight line with constant velocity if and only if the net force acting on the object is zero. Okay, that was quite of a mouthful, but let's dissect that a little bit further. Let's look at the first statement in a little bit more detail. An object that is at rest will remain at rest if and only if the net force acting on the object is zero. Well, let's look at these two players at rest currently with their tug of war, and they are only at rest simply because each player is pulling at each other with an opposing force, that is F1. If we just add the net force, we're just going to get F1 minus F1, because they are both pulling in opposite directions. The net force is zero, therefore the system will remain at rest. Nobody's going to start moving. I think that's a bit easy to understand. Let's look at the second statement. An object that is moving will continue to move in a straight line with constant velocity if and only if the net force acting on the object is zero. Okay, well, we have to dissect this a little bit further because we have to define that velocity has a speed, its magnitude, and direction. If any one of these two change, there has to be an acceleration, and therefore a net force on the object. Okay, let's look at an object on the surface of the circle spinning at some angular velocity. This point A is going to have some tangential velocity. That's going to be the tangential velocity. Its magnitude is going to be constant, however, the direction is always changing since it is going in a circle. Therefore, there has to be a net force acting upon point A, and that is just going to be simply the tension. That's what's holding it together, and that's what's keeping it going in a circular motion. It might not seem a little bit intuitive that it is accelerating towards the circle, but hey, that's physics for you. The second law of motion is simply the addition of all net forces is equal to the mass times acceleration. And I have these little arrows on top of the force and acceleration because these are going to be treated as vectors. Let's look at some examples. Let's say we were thrown out of an airplane and we are now skydiving. We are going to have a force that is going downward that is going to be the gravitational force. Let's say I reach terminal velocity. At this point, I'm going to have the maximum velocity that I can ever have while I skydive, and that is going to have a drag force equal to the gravitational force. So in this case, F net is just going to be the summation of the drag force minus mg, because that's going in a downward direction. And again, I am at terminal velocity, meaning I am not going any faster, I am not accelerating, so the net force is going to equal zero. Okay, let's look at an example where something does have a non-zero answer. Here we have a box that's being pulled 3 different directions, and let's use a little bit of vector algebra to figure out what is the net force. Okay, let's just start with the first force, F1. That's going all the way to the left, which is the most powerful force since it is designated by a bigger arrow than everybody else. That's going to be F1. Then there's going to be a tiny force pulling it upward with F2. And finally, there's a counter force pulling to the right, but is still smaller than F1. That's going to be F3. So, the net force is going to be like this. The net force. Therefore, the object will also accelerate in the direction of the net force. Hopefully this makes sense. all we have to do is add the net forces depending on their direction, and then we will figure out where the object is or is not accelerating, depending on if there is a net force. Newton's third law of motion says that every force acting upon an object will have an equal and opposite force. Let's look at this with an example from a classical physics lab experiment. Here I've drawn a little fan that is attached to a rolling cart. Let's say that the fan is turned on and starts blowing wind to the left. That is going to create a force that also pushes to the left. I'll say this is F1. And because of this, again according to Newton's third law of motion, there will be an equal and opposite reaction force in the opposite direction, which is also equivalent to F1. Because of this equal and opposite force, the cart starts to move to the right. Now let's say we have a plate in front of the fan, and the fan is turned on, and once again, air starts to blow to the left. Now this time, the plate that is attached to the cart will again feel a force to the left, F1, and the equal and opposite force, again, is going to be on the cart that wants to move to the right at a force F1, but this time the cart will be stationary. Why? Because the metal plate is attached to the cart and is feeling a force to the left, but at the same time the cart also wants to move to the right. So the net force is going to be simply 0, because F1 minus F1 is just 0. Let's look at a different example and let's put some numbers to play. An 80-kilogram football player on a frictionless ice pond throws their 200-gram phone at 25 meters per second squared to reach the perimeter that is 10 meters away from them. How long did this take? Okay, well first things first, let's look at the forces being applied to the phone. We're going to have some mass, the mass of the phone, being thrown at some acceleration. I'll say this is AP for the phone. And the forces, according to Newton's second law, is just MP times AP. Okay, now according to Newton's third law, this exact same force is being applied in the opposite direction to the person. So what I'm trying to say is that F sub P, the forces on the phone, is equal to the forces being applied to the football player. If we just expand both of these terms further, we're going to get the mass of the phone times the acceleration of the phone is equal to the mass of the football player times the acceleration of the football player. If we solve for the acceleration of the football player, we are going to get MP times AP over MF. Now that we have the acceleration, we can use one of the handy-dandy kinematic equations to solve this problem, which is simply delta x is equal to 1/2 at squared. We're going to say that the initial velocity is 0, so just plug in AF and finally solve for t. That's just going to be t equals the square root of 2 delta x over AF. And once we plug everything in, we are going to get 17.9 seconds. It's going to take the football player quite a bit to get to the perimeter, but hey, at least they're not stuck anymore. Anyways, I hope this video helped you out to learn Newton's 3 laws of motion. Hope that helped everybody, and good luck out there.